Okay, I went through a problem in our Physics 1A class a couple days ago involving the work done by gravity on a pendulum, and I wanted to just go back through it because we made some mistakes when we did it. So we're going to calculate the work done by gravity on a simple pendulum. So this is going to be the point where our pendulum is suspended from. Our pendulum is going to have a length here that we're going to call L. So this side will also be L. And we're going to look at the work done by gravity as the mass moves from this location here down to this location here. All right? So that's our mass. Now, in order to do this, we're going to need to draw some additional lines on here. We're going to need to draw a vector to represent the weight, which is going to point straight down like this. And we'll just label that to be our weight vector. I'm going to use the W and put an arrow above it. Because what we're ultimately going to end up doing here is we're going to be doing an integral of f dot dr in order to find our work done by gravity. We need to do this because we're traveling along a curved path. The path that we're traveling along is basically right here. This is our path. And we're going to parameterize, or we're going to break that path up into little line elements called dr. So let's draw a vector for those as well. And the other thing I want to do is to figure out a way to write this. Now, when we did this in class, what I did was I said that this angle right here we would call theta. And we found that by using this angle theta and then going through our integral, we basically got the wrong sign for our answer. We got the right answer, but the answer had a negative sign in the wrong place. So I did a little bit of work to understand why this was true, and I remembered that when you're doing these type of line integrals, it's really important that you make it so that the order of integration that you end up doing ends up being positive. And because of the way we defined theta, the initial angle was this big angle, and when the mass moved down to here, the final angle was 0. And so since we integrated from theta to 0, that's part of why we got the wrong answer. And I could just say, well, you just need to flip the limits, and there's a good reason for that. The other thing I could say is that the way in which the angle changes is negative, and that also allows you to get the right answer. But I wanted to do it in a different way because I didn't really feel super satisfied with a lot of those answers. So what I'm going to do is I'm just going to make sure that we use an angle that's defined in a way that you're more used to, which is to define our angle relative to the positive x-axis. So what I'm going to do is I'm just going to call the angle between here all the way up to here. We'll call that angle phi. But before we do that, I want to get an idea for what our dr should look like. And the way we're going to do that is I'm going to take another line and we'll draw it from our origin. Oh, we want to use a vector now. Let's describe how our position vector at any point on this circle could be described. So this is going to be a arbitrary position vector drawn in the first quadrant. We're going to define this angle right here to be phi. And then we're going to say that if our vector r were to shift up to a new position, then dr would point perpendicular like this to our path, just like it does down here, okay? But we're going to do it in the first quadrant because I think that makes things a little bit easier because we're dealing with angles that we can kind of visually see. Now, what I'd like to do is I'd like to write r in terms of I hat and j hat. So to do that, what we can say is that our r vector right here, in terms of I hat and j hat, if we make a little triangle, then this side of the triangle would be the length of r multiplied by the sine of phi, and this side down here would be r times the cosine of phi, which means that we can write r in terms of our I hat and j hat vectors as, well, the x component would be r cosine phi, and the y component would be r sine phi times j hat. But in our equation here, what we have is dr. So what we want to do is we want to differentiate this with respect to phi. So there's an r in both of these terms, so I'm just going to pull that out in the front. So the derivative of cosine phi will be sine phi, or sorry, negative sine phi, times I hat. And then the derivative of sine will be cosine. Oh, I wrote a j here, sorry. Sine phi would be with the I hat, and then cosine phi will be with the j hat. So now we have a way of writing what dr is. And I'll just shift the d phi to the right-hand side so that this becomes dr is equal to r d phi times all of this. There we go. So now we know what our dr vector is going to be. And this dr vector should work whether we write it up here as I did in the first quadrant, or whether we write it down here. This should work at all points along this circle. Now, f, in this case, is the weight vector w, so we also want to write that one down. That one's easy. The weight vector is going to be equal to the mass of our object times gravity, that's the weight, and it always points in the negative j hat direction, right? All right. So now what we want to do is to kind of evaluate this integral. So we have the work done is equal to the integral of our weight vector dot product with dr. And in terms of the variables that we have right here, when I do the dot product of this vector with this vector above here, j dot I hat gives us 0. You only get something when you do j hat dot j hat. So that means we're going to have mg times r multiplied by d phi and cosine phi with a negative sign. So I'll put the negative sign on the outside, and we just left in the inside with an integral of cosine phi d phi. I think that's correct. There's a negative sign. This negative sign shows up, mg shows up, this r shows up, and then d phi and cosine phi. That looks correct. So this ends up being the work done by the force of gravity. We could even indicate this is the work done by gravity. So now we need to think about what our limits need to be here. And the advantage of defining our angle relative to the positive x-axis means that we can make it so that our angle increases, which is basically required as far as I understand when you're doing these type of line integrals. You need to have it so that the parameter that you're using for us, which is theta, needs to increase in our integration. So in order to make that happen, we need to think about what our limits are going to be. So I guess we need to use a new variable now. And the variable we could use, I guess, we need another variable. We can use the gamma or something like that. So our initial angle is going to be from here around to here. I wanted to make that a different color, sorry. I wanted to make that green. So this is going to be our lower limit. I guess what I could do is I could say we want to go from phi initial to phi final. And our upper limit right here at phi final, you can kind of see that it's going to go all the way around to here, because we're going from from here to here. So phi final is going to be 3 pi over 2, or 270 degrees. And our phi initial is basically going to be 3 pi over 2 minus this angle theta. So those are going to be our limits. So let's plug those in here. I guess I have enough room to keep writing. Go down just a little bit. So we have WG is going to be equal to negative mgr. I guess we could go ahead and just do the integral. So the integral of cosine phi is going to be sine phi, positive. And then we just need to throw our limits on here. So I don't know why that happened. I think we got ink to shape going on. Turn that off. Sine phi, we're going from phi initial, which is 3 pi over 2 minus theta, up to the final, which is going to be 3 pi over 2 So now we have an increasing. This is good. This is smaller than this one. And so this should be equal to negative mgr multiplied by the sine of 3 pi over 2 minus the sine of 3 pi over 2 minus theta. And the sine of 3 pi over 2, since it's going to be in this quadrant down here, is going to be negative 1. Oops. So this first one is negative 1. And you can use one of the sum and difference formulas, so, you know, sine of A minus B, to prove that the sine of 3 pi over 2 minus theta is equal to the negative cosine of theta. So if we replace this with negative cos theta, there's a negative sign right here. So we're going to get plus cosine of theta. And then our final answer for the work that's done by gravity along this. Oh, you know what I did? I just realized something. The length of R is actually L. So here, when I did this, everywhere that there's an R, this should be L. I kind of want to just go back and fix all these things. So this should be L, 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 L. Anywhere there's an R, it should be an L. Sorry about that. Just go back through and do it, and I'll put it back in red to indicate that I made a mistake. So you can see this was an L, that was an L. There should be an L in front of all of these. Hopefully that's that, because that was the length of this vector R. My bad. L and L. Okay, so our final answer that we end up getting then, we multiply the minus sign through here, is m times g times L. And that's multiplied by 1 minus cosine of theta. And the good thing about this is that, unlike the answer that we got in class, this number is positive, because cosine theta is a number between negative 1 and positive 1. In our case, because of the way that we defined our angle theta here, cosine theta is guaranteed to be a number that is between 0 and 1, because it's an acute angle. So that means that this is a positive quantity. In addition, if you calculate the change of potential energy due to gravity in this situation, and we need to draw one more line to do this, by drawing a line here, where we say that this is our initial y-coordinate, and we say that this point right here is going to be our final y-coordinate, then you can prove that y initial is going to be equal to L times 1 minus cosine theta with a little bit of algebra, or a little bit of trig, which we did in class. And since the change of potential energy is mg times y final minus y initial, putting all of that together, this piece is 0. Plugging in L minus L cos theta into here, you get m times g times L times 1 minus cos theta. But there's a negative sign here, and that shows up right here. And this is ultimately what I wanted to do at the beginning of class yesterday, but I made a mistake. So that's why I'm uploading this now. And when you compare these two, you can see that it satisfies what we know for conservative forces, which is that the work done by the force of gravity needs to be equal to the negative of the change of potential energy due to gravity. And so there we go. Just another way to solve the problem we did in class, except we defined the angle as positive relative to the positive x-axis, and that guaranteed that we got the right answer. I did find out that part of the reason why we got the wrong answer in class was because if you make it so that your angle starts here, and you use theta, so what we did was we did an integral from theta down to 0. The error that I made was that d theta, which shows up in your integration, should have been negative, because theta is actually decreasing. And that was the mistake that I made in class. So anyway, here you go. Here's a more proper solution, and hopefully that addresses any of the issues that you might have had when we went through this in class. So thanks.